One is known as correlation and one's known as regression. Before we just give that away, let's briefly kind of understand the overall scope of everything. So on unit 1 or test 1, the whole thing was all about what is this thing called center, mean, median, mode, range, all those kind of calculations, and distribution, and how that impacted what we called center. Discrete distributions, continuous distributions, all the different kinds of distributions, and how we calculate different values about them. Then the next big thing was all about how to find the probability given that we know the center and that we know the distribution. So if I knew I had a continuous distribution that was normative, how did I find the probability of some number less than or some number bigger than? If I knew I had a binomial situation, how did I find the probability, and et cetera, et cetera, et cetera. Third major topic, the one that y'all all just did, was how do you verify what you think is the center? So how do you verify the center, aka the null hypothesis? How do we check and see if it seems to be consistent and accurate? And so that's kind of like the whole point of that. And then, of course, we did that through confidence intervals, hypothesis testing, and all that fun stuff. And now this final unit, I call it, even though it's really just about 2 lessons, 3 lessons, but this following unit now assumes that we've done all 3 of those things already, that we know what the center is, we know that we were able to kind of find enough evidence to verify it, and then what's the implications if that's true. So a classic example I like to give is something like age versus height. And maybe we established that at age 5, we were able to verify that someone who's 5 years old, I'm making these numbers up, but maybe like 2 feet tall. And then we go through and we do some studies, we find out that that seems pretty consistent. And then we go and find a 10-year-old group, and we calculate their height, and maybe they're like 5 feet tall. And again, I'm making these numbers up, but let's just assume that they're 5 feet tall. And we were able to establish, we did the hypothesis testing, all these numbers seem to be holding true. Well, we understand that age is a progression. You don't go from 5 immediately to 10. So you're not going to just like warp from being 2 feet tall to immediately being 5 feet tall. There has to be some kind of growth between these two. And so it might be a straight line growth. You might grow real fast and then slow down. You might start off slow and then kind of speed up. For our class, we're going to assume in general this straight line growth. And that straight line growth is known as linear. And so when we're talking about this kind of straight growth, we're just calling it linear for, line. But linear is just like the noun version of that word. Just trying to write that a little nicer. Very little nicer. But the cool implication about this is that notice that we only established that we know 5-year-olds are 2 feet tall and we know 10-year-olds are 5 feet tall. That's all we actually know. But because we know that there's some kind of pattern between these two, we now get all this free information without having to go through and study and verify and collect samples and all that stuff. We know that from 5 to 10, we progress naturally. So there has to be a height between there that belongs to 7-year-olds and a height between there that belongs to 9-year-olds. And we get this information for free without having to go through the whole analysis process. And so that's kind of the point, is that we're able to kind of use facts that we know and then find facts between the facts. What we cannot do with this data is we cannot talk about anything before our data started. So we can't talk about anything less than 5 years old because we have no idea what happens there. We didn't verify that direction. And we can't talk about anything after 10 years old from this situation because we don't know anything that's happened beyond our data. The only thing that we know is from 5 to 10 years old. So you're only allowed to talk about this range from 5 up to 10, because it may turn out that after 10 years old, we kind of flatten out and stop growing. As y'all know, when you turn adults, we don't really get taller after we become an adult, right? It may happen that Once you get to a certain height, maybe we start shrinking. As you get older, your bones kind of decay a little bit. Or it may happen that we actually continue going straight. We don't know. All we know is what happens from 5 up to 10 in this story. So one important concept to get is whatever your bounds are is the extremes that you can talk about. You can go as low as 5 and as high as 10, but nothing beyond those two boundaries. Hello, everybody who just showed up. Okay. And I see some familiar people from Tuesday. Just a FYI, this is the same presentation from last Tuesday. Next week is the new presentation, but if you want to catch it still, that's fine. But let's continue. So that's the kind of general idea of what we're doing now, is if we can establish that we have a linear relationship, we want to be able to use these facts to make predictions about things going on between our points. That's the kind of big idea of what's going on. And so a good question might be is how do we establish that there is a linear relationship? Well, we look at generally 3 things. And so 3 things tell us that we have a good relationship and good linear relationship. And in general, when we say a good linear relationship, we're essentially saying that we have a good model. And someone says, do you have a good model? This is what they're asking you. Do you have a good linear relationship? Because we're going to assume for this class that we're talking about linear models, straight line models. There we go. And so what 3 things do we look at? The first one is we look at the scatter plot. If it has a good linear model, then what we should see is one of 2 things. You're going to see random dots because we have variation in our data, but they should all be going in a similar direction. In this case, they're all kind of going up and to the right. We call this a positive correlation. And likewise, if they're all kind of going down, and you might have a few outliers, but in general, they should all be kind of following a nice pattern. Maybe not that extremely different though, so I'm gonna kind of back that off a little bit. But you can have like, points here like this, that's okay, as long as it's kind of close to the line. When it's going down, we call that a negative correlation. What is bad though, in terms of a scatter plot, what would be a red flag, is if we saw patterns that were not linear. So if you saw like a rainbow, that's bad. If we saw like a wave, these are all signs that they're probably not linear relationships. And then the third one is if there's like no relationship at all. It's just pure randomness in every direction. So this implies non-linear because you can't draw a straight line and hit your dots. You got to draw a curved line. This is also non-linear for the same reason. You have to draw a curved line to hit most of the dots. And this one is just pure random. We call it no relationship. And you'll learn in your class why or what makes these things or why we would say it has no relationship. But, just in general, it's just how when you look at it, you say, okay, no relationship. But you'll learn in class, when you get there, what this stuff, what kind of situations would cause this and that kind of stuff. But these 3 on the left, these are examples of bad scatter plots. Actually, just do it this way. We'll just group them and just say bad scatter plots. And all I mean is that they're examples that this is going to be a non-linear or not linear relationship. And so if you see the bottom 3 problems, you see the top 2, good. And those are examples of good ones. And so we need that happen to have good models. The second thing is our R² calculation, which we'll learn today how to do it. But R² And I give you the name of it and the definition right here. This is the actual official calculation, but over to the left, you can see the description of it. The big idea here is R squared is a calculation of variance. And it essentially tells us how good that line matches how the data is changing. And so when we draw these lines, the data is usually not in a very perfectly straight line. And so the more close the data is changing in the same kind of shape of the line, the higher the R squared. And so the higher the R squared, the more better the variation is being described by that line. And so essentially, we'd want a high R squared to represent a good model. So what's considered high? That's the tough part. It is very much industry dependent. And so like if you're in education, because there's a lot of different variables that affect someone's personality or their learning or whatever you're measuring, they tend to accept the lower R squared, something like 60, 70%. If you're in like safety industries, they want a really high R squared, like 80 or 90%. So it's kind of hard to tell you what is considered really a high R squared. Now, there is what they call R squared hypothesis tests. And we're not going to do that in this class, but I have seen a few professors assign a homework that kind of gets at that. I don't go over that because it's never going to be on the exam, but some of y'all may get questions like that for homework, in which case I'd be glad to show you how to do it. Just come to my online drop-in or come to my center and I'll show you how to do it. But I don't tend to do it in the boot camps just because it's not relevant to the exam, and this is all about how to learn the material to be successful on the exams and that kind of stuff. So there is a formal way of talking about this, and it depends on degrees of freedom and all that stuff, but I'm not going that deep into it. For us and today, we're just going to define R squared as being high if it's greater than 0.8. Now, obviously, if your teacher tells you a different threshold, greater than 0.7, greater than 60, whatever, like 60%, then do what they say. But just for us today, as we talk about some problems, I'm going to use that as my threshold to represent high. And so anything lower than 0.8, I'm going to say is not that high. But again, this number was arbitrary. I could have very well said 0.7 or 0.6 or 0.50 for gosh sakes. It really just depends on the industry you're in, what's accepted practice, often the sample size, whatever method you're using. The R squared p-value method that you'll see for some of your homeworks is very much from the science field and what's considered acceptable in the science field, but that's not universal. And so it's just what we're going to define for today. And then the third kind of calculation that's really important is residuals. Residuals is what we call direct error. And the actual calculation is the actual y minus our estimated y, or predicted y. And we often call that symbolically y hat. And so we're going to take the actual event that we have data for, and we're going to subtract off what we predict and see what happens. That calculation is a residual. And what we like to do is plot all these calculations, all those residuals versus error. And so, of course, there could be zero error where there's no mistakes at all, or we could have positive error or negative error. And so we just get some dots along here in different spaces, of course. And the idea is that what's happening is if I draw a line like this, maybe, and then we have our data around that thing, a simple positive correlation. What it does when you do the calculation is it measures how much error there is here, how off our prediction, that's the prediction, and this is the actual. And so if you measure that distance, let's just call this distance here. Maybe this was an actual value of 6, and that prediction says it should have been 4. So the error is 2, right? It's 6 minus 4 is 2. So what would happen then is it would graph, if this is my location at, let's say, 3, it would come over to where 3 is, and it would go up 1, 2, and put a dot. And so that dot would just represent how much error there was from what we said was actually happening versus what we think should happen. And then the next location, let's say this is like a 3 and that's a 1, it's now down 2 places. So at that location, maybe 4, it would go down 2 places and put a dot. And so these dots just represent what was the mistakes from the line to the dot. And the goal is that our line should be slicing our data above and below, kind of right down the middle of our data. Because remember, the whole point of all this is to find the center. And so the goal is to have about as many above as you do below. It should be approximately equally split. And so if it's equally split, just approximately, because you're going to have odd numbers, so you can't always have it exactly equally split, but it should be about as bad above as it is below. And that's a good sign. The second thing that we should see is randomness. We want our dots looking kind of chaotic and all over the place because we don't want to kind of have any kind of pattern forming. If a pattern forms, you'll learn more about this in your class, but if a pattern forms, it means that there's some kind of other relationship happening with the dots that you're not capturing with that straight line, that there's some kind of curving or nonlinear behavior happening. And so if we have it random and equally split, that's a good sign. A bad sign of a residual, just like your scatter plot, is if we saw dots that make a pattern. That, of course, means that there's like some kind of curving behavior that you missed on the scatter plot and that kind of stuff. And so this is a sign of a bad residual. Another example of a bad residual is if all the dots are up here. That means for some reason your line is too low and it's missing all the data and it's undervaluing. That tends to happen when you have an extreme outlier. And so like if I had one random dot way over here, what that one dot will do is it'll pull, because we know what happens to means when you have a line like that, it'll pull my line down. So now most of the data is way, way up above what's happening because of that one outlier. And so then you'll have something like this, where almost all the data is definitely not equally split. It's way too high. And so that's a red flag that there's something wrong with your data. In this case, an outlier. That kind of stuff can happen. So residuals, to recap, should look random and about equally split. They can be off by 1 or 2, but just generally. R squared for us is going to be greater than 0.8. Obviously, whatever your teacher tells you, use those numbers. So you definitely need to check your class out because that number is arbitrarily defined. And so whatever your teacher defines it as. And then for scatter plots, we have a positive correlation or negative correlation is what we're looking for. Or the other 3 here are examples of bad relationships. Okay. Now, let's actually talk about a couple other things before we get there. You can see on page 105 is your in your lab manual is where all the formulas are. And you can see for this last section, there are 3 new formulas. And you'll notice that the bottom 2 want us to enter y values and then x values. While the first one doesn't require that, you can enter it in either direction. Array just means a list and a list. And so they just want you to list your numbers out in 2 groups. They don't care what order you do. Because these require y's and then x's, you will see me always do y's and then x's, just so I have less things to think about. Because these require it that way, I'm always going to do y's and then x's. But it really doesn't matter which way you do it for correlation. But just so I'm consistent and not having to think about things, I will always do y and then x. That's the first thing I want to mention. The second is this slope and intercept part. This is actually getting at the linear regression, sometimes called a least squares regression. You can see that right here. line. It's the elements that calculate it. And so the formal definition of it, you may remember from high school, we would call it y equals mx plus b. That's the linear regression line. But in statistics, we write it a little bit differently. In statistics, we like to write it as y hat, because we're predicting or estimating, equal to this b first, and we often call it b naught, plus or minus, depending if the slope is positive or negative, of our slope, which we call b1, and then x. So this m is the b1. So that's the formal way we do it in statistics. Why? Because we want to be extra. There's no real reason mathematically beyond the fact that this just makes a lot of sense for us and how we interpret things. And so this b naught, that's known as the intercept. So there's your b naught calculation. And the b1, that is known as slope. And so what b naught actually means in the real world is that is our starting value, or our initial value, where this represents the change per 1x. And so a simple example of this is, let's just pretend that we have the following equation: y hat equals 3 plus 2x. What this is telling us is that we start at 3. So at the beginning, at time 0, we have 3. And then this 2 is telling us that we're going to constantly add 2 to the y's. So the next value is 5. The next value is 7. The next value is 9. Next value is 11. On and on and on and on, per 1 extra x. And so x's will always grow by 1. So per 1, per 2, per 3, per 4, and so forth. So for every additional one of these, we grow by 2 of the y's. So the y goes up by 2 every time. And so if I had y hat equaled, let's say 10 minus x, or just say 4x, something more realistic. And I'll say 100 instead then. There we go. So we're saying that we're going to start at 100. And of course, x's always grow up. We always go up by 1. And we're going to go down then, because this is minus 4. We're going to go down by 4 each time. So 100 minus 4 is 96. 96 minus 4 is 92. 92 minus 4 is 88. And so on and so on and so on. So all this number here represents is how much it's changing each time you go down. It's going down by 4 for every additional x we get. And that's the idea there. Okay, so that's how the model works. Now let's talk about this other term right here. And then we'll jump into some practice problems, and then we'll be done for the day. So correlation, also known as the correlation coefficient, is the calculation of R. And I gave you a chart here, but like R squared, because they're actually variations of each other, one's just the square root of this calculation, it's arbitrary. And so you may have a different chart from your teacher, so definitely check your class and see if your class uses a different chart, but this is something for us to talk about today so we can articulate what we're doing. But in general, this is kind of like a general understanding of what R is. And notice that we use the same words when we describe it, whether positive or negative. Weak, moderate, strong, very strong, weak, moderate, strong, very strong, whether you go negative or positive. And then, of course, no correlations when you're close to 0. So then why do we care about the pluses and minuses? Well, remember what I mentioned earlier. If it's a positive correlation, that means the data goes up to the right. And if it's a negative correlation, it goes down to the right. So over here, notice that when we have no correlation, we just see a bunch of random dots with no real pattern. But then notice now in the next one that they're slightly increasing. I can kind of box them. And we can see that it's still kind of chaotic, but they're kind of still drifting upwards. We don't have anything down here and we don't have anything up here. So it's kind of definitely going in that direction. And then likewise, it's in general going down, but still not quite close together. And then notice that as the dots get closer and closer together, these are much closer than the previous ones, the R value starts going up. And so this R value, when it refers to its strength, it's referring to how close the dots are to each other. And so as the closer and they get closer and closer to a straight line, that R value gets closer and closer to 1, to where eventually they can become virtually exactly straight, in which case we'd call it 1. Or if it goes very straight but down, we call it -1. So the higher the R value, the more straight the data appears and that kind of stuff. And that's correlation. And one other thing I want to mention, just to kind of put all this stuff in a nutshell, is when we have our X value and our Y value both changing in the same direction. I don't care if they're both increasing or both decreasing. If they both change in the same direction, we call that a positive correlation, period. And if they change in opposite directions, we call that a negative correlation. And so we've already actually dealt with examples of this kind of idea. We just didn't use this language when we talked about them. Remember on test 2, what happens as sample size increases? Well, the confidence interval decreases. So that's an example of a negative correlation. And likewise, if the confidence level increases, not sample size, the confidence interval increases. So that's an example of a positive correlation. Now, I did include an extra little thing over here. You'll see that when I post it in the chat, just something to read through. It gets at the fact that you have all this data that has the exact same mean, same standard deviation, and all that fun stuff. But it gets at the fact that you have to look at the scatter plot to see that these things, even though you can have all the same calculations, you can have completely different results if you're not looking at the scatter plot. It's kind of the idea of why we look at a scatter plot for a model. But here you can see that in general, we have a pretty positive relationship, a very positive relationship with this random outlier going on. And then here we have a curved relationship, which is a red flag that is probably not linear. And then again, very straight with this one random outlier. And so these kind of things would have really differing models that would either be great or not great. Mainly, the only really good one is this very first one, because all the dots are kind of clustered around that line I just drew. While the ones with the outliers, the line would drift towards the outlier, meaning that we would have a lot of bad predictions, because all this data, is not near the center at all where the data is actually happening. And you'll see all that today when we go through some examples. But anyways, read through that. That's just a nice fact to remind us the importance of looking at the scatter plot. Okay, whew. Let's get into some problems. There's a reason why I only give us 5 problems today. Okay. Some throwback to test 1 in some terms. The explanatory is, of course, what we're trying to use to explain something else. So we're hoping that this can explain a response. So in other words, this is our X, and this is our Y. And for those who may not remember from high school, X goes on the bottom, Y always goes on the side. And so X is considered what we call the independent variable. Independent. While Y is the dependent. In other words, we're trying to say that X can somehow dictate what happens in Y. Maybe not causally, but as X happens, Y should happen as well. So it might just be correlated, but not necessarily causated. So we're not saying that one makes the other one happen. We're just saying that if this event happens, we seem to find the other one happens in the same manner. You know, if one's increasing, the other one's increasing. If one's decreasing, the other one's decreasing. Or I shouldn't say the same manner, because if one increases, the other one could decrease. Just that there's a common pattern that as one changes, the other one changes in some way at the same kind of rate that they're both changing. You'll see. But the idea here, the story that we're trying to see, the explanatory, obviously, since that's the bottom, is the egg volume. And so a good thing to note is the bottom will always be your explanatory. And so the response is that the bill length. And so essentially what they suspect is that eggs, if they're bigger, because you can see it kind of going up, if eggs get bigger, then bigger bills are on the birds. You know, essentially, if you're a bigger baby when you're born, you'll be a bigger adult. That's the idea that they're going after in terms of birds in this case. And likewise, the smaller the baby, the smaller the bill, because we see as a positive correlation, we would assume that they're changing the same direction. So bigger babies, bigger bills, smaller babies, smaller bills. That's the idea of what's going on here. So they're hoping, if this is accurate, that egg volume is describing how big the baby is. When we describe a scatter plot officially, there's three things that we look for. First one we call form. Sometimes you'll hear the word type. I believe your class actually calls it type. The second thing we talk about the strength. And then third thing we talk about the direction. And so the form or type, you can look at the line itself, what kind of line was used. It was a linear line. They didn't use like a big curved line for nonlinear. So for our class, we would either say linear or not linear. That's our two choices. Let's write them both down so we can remember what the choices are. We would say linear or nonlinear. In this case, we chose linear because that's a straight line. The strength, you would technically need a value so that you can actually pick the appropriate strength word. So this down here, that's known as the strength. And so if you knew what the value was, you would say, okay, my value is 0.3, so I would call it weak. So when we say, you know, moderate, weak, strong, very strong, those are strength words. Obviously, we don't have a number, but if we went to our kind of like rough sketch of the drawings here, you can probably, hopefully agree that it's somewhere between 0.3 and 0.6. It looks like it's between one of these two, probably closer to this kind of example, but that's just rough sketching without an actual number. I would actually have no idea what number to put here, but if you had a value, like maybe we said this was R 0.6, making that up, but you would need to know that number. You would then go to the chart and figure out 0.6, 0.6. Okay, that's right about here. So I could call it moderate or strong. And in fact, it would really be exactly 0.6. So let's just say that was 0.62, in which case that's between 0.6 and 0.8. So I would call it strong. So again, just to be clear, you would have some kind of R value. And so the strength would be, in this case, strong if that was the R value. I made that number up. Without it, we don't actually know. And then the direction. Is the line going up or is the line going down? It's going up, so the direction is known as positive. So the official description is that we have a strong, positive, linear relationship. It doesn't really matter what order you write these adjectives in, unless your teacher tells you, but we do generally say the linear part last. And so some would say positive, strong, some say strong, positive. For me, it just rolls off more naturally to always say the strength first, and then the direction, and then the type. But there's technically no formal way that you have to do it. Just whatever sounds best for you. For me, linguistically, it just sounds better in my head to say the strength, direction, and then the relationship. But whatever works for you. Okay. I know I'm going overboard with my details, but I just like to make sure I really hit home what's happening here. Next part. So this C case says, suppose we add in this extra bird that has this bill length and this volume. What would be considered unusual? Well, 183 on the volume, that's around here somewhere. And 9.5 on the bill, that's there. So where those two things meet is over here. And so what's unusual about that from our model? Well, remember this line here, this is where we're predicting most of the points to be near. And you can see for the most part, you know, these points when they're off, they're not that far off. These are relatively close to that line at each spot. And that's the kind of idea that it should be relatively close. But then we have this one random new point. That is very far away from what we said would happen at 8.5. 8.5 birds should be way up here. And so that distance would be a red flag. Because that's way different. And so what's unusual about it, how we would just describe it for this class, because we don't need to do any kind of heavy analysis for this class, at least not for this unit, is that what's unusual is it is unusually low. It is way, way lower than what we would expect. We would expect birds of that size to have much bigger bills. Like I said, based on this data, it appears bigger bills, bigger volumes, bigger eggs have bigger bills. And this is a very large volume, 0.83, way over here. Most of the birds are clustered around there. And we have this volume up around, it should be around 10.5, and it's only weighing 9.5. So it is unusually low. It is much less than what we're expecting. And so, of course, that would require us, if we wanted to go do a hypothesis test and see if that value is contradicting what should be happening. That would be essentially a test we would do. In the real world, that would be our null hypothesis. That would be an example of our, data. We would get a bunch more and generate an X bar and find out, is the line actually not linear? You're not going to do that in this class, but that's essentially what would happen. And then you could find out and verify what's going on. But yeah, that's just an unusually low value. It's a sign that there's a possible red flag, or if that was actually a real answer, that what actually happened and there's nothing unusual, then it'd be a sign that maybe our line is in fact not linear. And so that just seems to be very unusually low based on what we're seeing from the rest of the data. Okay. Now we're being asked to determine the correlation between two variables without any calculation whatsoever. And then, of course, we will do the calculations just to verify, and there it is. They want to talk about the type, strength, and direction. And so we'll do that too. In the first example, you'll see that our input values, these x's, generally goes x and then y. But also you can think about it kind of like cause and effect. Would hours spent online affect your test grades, or would test grades affect how long you spend online? In general, we're talking about how much time you spend online relative to test grades and that kind of stuff. So it would kind of be like dictating it in that direction. But by convention, whatever's first is usually your independent variable, and whatever second is your dependent variable. So now looking at our data, though, what do we notice is happening with the x's? In general, or in this case exactly, they're always increasing. They're always going up. X is always increasing. And in general, for Y, it's 90s, then 80s, 70s, an outlier, 60s, and then 50s, and 60s, and 50s. So in general, it starts high, and then it goes pretty low. So the Y's are decreasing. Well, when they change in different directions, that indicates a negative correlation. I don't know what the value is, but I know it's going down in general. Now, of course, you're going to find exceptions because we have variation. It won't always be strictly decreasing. If it was, that means our R would be exactly 1. And so the fact that we have a few mistakes here and there indicate that the R is not going to be exactly 1, but it still should be a negative R. And if it isn't, that's a red flag that something's wrong. Now let's calculate it. Our first real calculation of the day. I'm going to erase my lines here so I don't have any problem highlighting. And what we'll do is equals correl y values and then x values. Close it, hit enter, and there's my negative correlation. And if I want to describe it, we did correlation. For this class, we're going to assume linear. Obviously, you wouldn't know without looking at a scatter plot, and we can actually do that in a little bit just to verify. And then, of course, our sign here is negative, and our strength is 83, and that is in the very strong category. So we would say very strong. So we have a negative, very strong linear correlation. That's how I would actually say it. If I wanted a scatter plot, I would highlight my 0 through 50, go to Insert, pick the scatter plot option. It's called Scatter. Pick the very first one, and there is our scatter plot. And we can see that it does look to be relatively straight in this downward direction. Okay, that's the first one. Now let's look on the next example here. Same idea. One thing you'll notice, though, is our x's are not in order. Usually, in order to interpret this, it's more beneficial to make sure your x's are in order before you try to do the problem. Otherwise, it gets very complicated. So what we're going to do is copy our data, because you can't sort it sideways. So we've got a nice little trick for that, though. We're going to copy our data, then we're going to right-click in that empty area. And then when we look for our paste options, we don't want to do a normal paste. We want to go to the paste that has the little arrows called transpose. The transpose paste turns your data vertically. That allows us to sort the data now. So we can go to Home, and we can sort it by clicking the smallest to largest option. And now our data is in order by X. It doesn't order the Y, it only orders your first column there. So X is now definitely increasing. What is Y doing? Well, it starts in the 30s, then it kind of goes up 40s, 60s, 80s, 90s, and we can see it's going bigger and bigger numbers relatively. So in general, overall, it's going up. So notice they're changing in the same direction. So we could call this a positive correlation. And then let's actually get our scatter plot so we can verify linearity, verify that's a straight line. Insert scatter plot. And yeah, the dots are, they're going to be clustered about. So you're going to have some kind of randomness, but we have some kind of general straight line going through that way. So that seems to show that it's linear. And now we need our R value to actually be able to talk about the correlation. So let's see, equals correl, Y values, X values, 0.86. And so yeah, that matches our positive correlation prediction. And so we have linear, we have positive, and the 0.86 is very strong. And so we have a very strong positive linear correlation. And one thing I will point out is you might have noticed that this was negative, but I used the right side to predict it. I said, well, 0.8 is over here. That's because these are mirror images of each other. So positive 0.83 and negative 0.83 use the same word. And so if it was negative 0.83, that's the same kind of language, the same strength word as 0.83. They both would say very strong. And so we really don't actually need the second half of the graph, because it's literally, if you go to 0.2 or 0.2, we're going to use the same word. If you go 0.4 to 0.4, it's the same word in terms of strength. And so technically, since negative 0.83 is over here, I should have looked here, But negative 0.83 and positive 0.83 would have used the same word anyways, so you really don't have to. You just got to remember whether it's positive or negative, though. Anyways, there are our facts. It's linear, positive, and very strong. Moving on. Okay. Now we're going to talk about the model being appropriate. And remember, that's those things I was talking about over here. Do we have a good model? Do we have a good scatter plot, good R-squared, and good residual? And of course, a few of these, one or two of them, could be a little off. Like it could be 0.76. But if you have a good scatter plot and you got a good residual, you'll go with it. You could have a very good scatter plot, a very good residual, and if you close enough R-squared, it's fine. But if one of these things is outright terrible, like one of the very bad cases, then we would throw the model out. So in general, they should have at least 2 out of 3 of these be really good and 1 be questionable. That's fine. But if 2 out of 3s are good and 1 is just very awful, like nonlinear, scatter plot, that kind of stuff, then we would throw the model out. That's how we determine if it's appropriate or not. And so essentially, we're going to check out, just to be clear here, the scatter plot. We're going to check out R-squared, and we're going to check out the residual. And in general, we want all 3 to be good in the ideal situation. And if not all 3, at least 2 of them need to be good and 1 needs to be close. But if any one of these is outright terrible, we would throw the whole model out. And we would call it inappropriate and do something else in the real world. In this class, you would just call it inappropriate and move on. Okay, so let's get the scatter plot first. Insert scatter plot. And so there we go. Does it appear to be going in a relatively straight line? Yeah, I would say so. It appears to be, relatively straight, really close to a line I can draw between them. So the scatter plot looks good. And let's get our R-squared. So R-squared is literally the R being squared. So let's get the R. R is correlation, right? So let's get our correlation, correl. And there's 2 ways to calculate this in this class. I'm just showing you one way. I'll show you the other way on the next problem. So there's R. There's actually more than 2 ways, but I'm just showing you 2 ways today. So correlation is just Y's and then X's, right? So we have our correlation. So R-squared is very literally that R that we just calculated squared. And so there is my R-squared. And notice 0.97. That's pretty high. So R-squared is good. We said for today's purposes, we're going over 0.8, and that 0.9 is definitely bigger than 0.8, so it's good. So we have a good R-squared. Last thing we're going to need to worry about is the residuals. So I'm just going to move these calculations over out of the way. And so a residual, once again, is just a graph of the errors relative to our predictions. So in order to get the predictions, we're going to need the equation of this line I drew. We're going to need the exact equation. And remember that line that I drew is of the form y hat equals b naught plus b1 times x. And so we're going to need these 2 numbers. Well, b naught, that's just the intercept, and b1 is the slope, and we have formulas in Excel for those. So intercept, y values first, and then x values. There we go. And now we need the slope, y values first, and then x values. So now I have my equation. I know if I wanted to write the equation out, I would say that it is y hat is equal to, let's just round that to maybe 1 decimal. And since b1 is positive, I would say plus point, I'm going to go 2 decimals here because the 99x. And yeah, that would be my prediction equation. So the first number and then the second one goes there. And so let's actually get our predictions. We'd want y hat, and we have equals. Let's make that font nice and large for everybody. We would have equals 1.7 plus 0.99. I did plus because the 0.99 is positive of my x times my x. And so what this is predicting that is that if we know this input, our answer should be about 58. Now, in reality, it was only 57, and that's okay. It's not going to be exact. It's just going to be close in general. That's the goal. So now if I take this all the way across, I get all my predictions really fast, and we now know what each value should be. And so it's predicting that at 59, it should be 60, and it was actually 59. At 61, it was 62, and it was actually 64, and so forth. And so we have the actuals, that's these y values, actual versus predicted. That's an A. Actual versus predicted. And so the actual minus the predicted, that's known as the residual. So we're going to simply do the actual event minus the predicted event. So what actually happened minus what was predicted to happen. These are the errors, how off it was each time. So now that we have our residuals, what we want to do is just graph the residuals. But the problem is that we want to graph the residuals relative to x. And if you just try highlighting it, you're going to grab too many rows. We only want to grab this first row and that last row when we graph our residuals. And one way of doing it is to highlight your x's by themselves, let go of the keyboard, mouse, whatever, hold down Control on your keyboard, and then highlight the other row the same way. That allows you to split highlight. You can highlight the first row and the last row and not the ones between it. So let's do that again. Highlight the first row, let go of the mouse and the keyboard or whatever you're holding on to, press Control, and then highlight the bottom row. Alternatively, if you don't like that, what you can do is you can highlight all this, copy, paste it somewhere. But when you paste it, you want to paste it as a value. So the paste 1, 2, 3 option. And then you can simply delete out the middle two rows. If I delete these, I now only have my first row and my last row. I'm not a fan of this method, but it does work. And so that way you can have your x and residuals next to each other and you don't have to worry about split highlighting and all that stuff. But let's try it again. Highlight the first row, hold down Control, highlight the last row. We can go to Insert now, Scatter Plot, and we get a residual graph. Remember, for residual, it's good if it looks relatively random and about equally split. And if we look, we see that we have about 5 of them below and 3 to 4 of them above. So it is about halfway. That seems to be pretty good on the split. And does that look like a pattern to us? Do we see like a rainbow pattern or some kind of, nice, easy wave? We don't, right? It's just kind of random dots all over the place. And so this is a sign of being about equally split and random. And so it's a good residual. So since all 3 things seem to hold up, it does seem to be good. It's a good graph. So that means we can actually now make predictions. We can predict the output when we know the input. So let's actually make our 2 predictions. Let's predict when the input is 60. We know it would be, making my font larger here, equal to 1.7 plus 0.99 times my input of 60, literally plugging it into the formula, and 1.7 plus 0.99 times 90. And there's our predictions. Now think for a second. Mathematically, my predictions are done correctly. I did everything right, but one of these answers is a mistake. And if you try to give one of these answers, they will mark you wrong on the test. Think for a second and see if you can convince yourself as to why one of these is incorrect. I'll zoom out for a second. See if you can think about it. Why is one of these a mistake? And I promise you, it's not my math. My math was done right. I calculated everything the way you're supposed to and all that stuff. But one of them violates one of our fundamental assumptions that I mentioned at the very beginning of this. Remember our scope. We can only talk about from the areas that we've already validated. So we only know what happens from this point to this point. We can only talk about the data between those 2 points. We don't know what happens over here. It might go flat, it might go up, it might go down. We don't know what happens after this point. We don't have a clue what's happening. All we know is between our smallest and biggest point. So on our x's, what was the smallest point? 45. What was the biggest point? 68. So we're only allowed to talk about calculations between 45 and 68. Well, 60 meets that requirement, but 90 is too big. That's called extrapolating, and there's a whole different technique for that. So this is bad. You cannot make predictions beyond the scope of your data. So you cannot go beyond 68. You cannot go beyond 45. That's the range of acceptable calculations. So we can calculate anything between 45 and 68, just nothing beyond that range. So even though the model is appropriate, the prediction is not appropriate because it's beyond our scope. All right. Now the same kind of question. Determine the acceptable range of inputs. So what is the minimum acceptable value and the maximum acceptable value? Well, looking at our data, we want to find the smallest x value. I hope we agree the smallest x value, that thing go away, is 56. Why is it doing that? And the largest x value is 80, right? So the range of acceptable values is 56 to 80. Anything outside of that range is simply inappropriate. So that's the minimum to maximum that we can talk about. Anything outside that range is inappropriate. So they can ask you for any calculation as low as 56 and as high as 80. You just can't do any calculation after that. So what do we do if we find out a model is not appropriate? In other words, when we went through that whole kind of check, what do we do if we have a bad scatter plot or a bad R-squared or a bad residual? What do we do if we can't use our model? Well, you actually already know this answer. So what are we saying if the model is not appropriate? If the model is not appropriate, it means that x cannot be used to describe y linearly. And if x can't describe y, how else do we know how to describe y? We would describe y as a single set of data. We would describe y by itself. And so if we want to predict what would be the most common value for y using only y, we would simply find the average of y. Because if we didn't know x, if x didn't exist, if it's not appropriate as far as we're concerned, if x is not appropriate and we want to predict the outputs, we want to predict y, we would simply say, well, with this data, my center is blank. And so, yeah, if we only had one set of data to predict something about y, you simply take the average of y. And so what is the acceptable output is simply going to be the average of our y's. And there you go. So on average, a y value would be around 202.9. That would be our general prediction. Because if we can't use x to describe y, then all we have is y. And the only techniques we have for describing y is mean, median, and mode. And for our class, pretty much we exclusively use mean. And so the most common approach is just to take the average of y. Now, in higher statistics, you would do other calculations too and decide whether it's skewed left, skewed right, and all that. But for now, for this assignments and stuff, if they tell you the model is not appropriate, just take the average of y. That's all they want you to do. Okay. Now we're going to determine the slope and the y-intercept. And I'm going to do it two ways this time, so you can see the other method. That's also a very common method. And you can kind of decide which way you want to do it. There are limitations on the second method, but it's still a very quick and easy method that's actually faster than the way I'm about to do it. So if I want the slope, I would just say equal slope, right? And then I can do the y's, and then the x's. And I have my slope. If I want the intercept, y's, and x's, and I have it. So what is this saying? This is saying that for every additional x, y, because this is positive, increases by 24.08. Right? So if every time I add 1x, I add 24.08. And what does this say? This says that we start at negative 1413. And so essentially, if I were to graph it, I would start way down here at negative 1413, and I would grow up by 20 every single time. Every line goes up about 2408. That's the change. Not asking me to graph it, but that's what it essentially is saying. Now, I mentioned there's another way of graphing this, and it's actually going to be how we're going to do it for this determining if the model is appropriate or not. The alternate way of getting your slope and intercept is to highlight your data, go to Insert, and make a scatter plot. And then once you have your scatter plot, what you want to do is right-click on a dot and add trend line. This menu on the right pops up. Our class, we use linear. And if you scroll to the very far bottom of this list, you'll see display equation, display r squared. And it gives you the same calculations, 2408, negative 1413.1. And it also gives us our r squared calculation. And what you can do is click on the box border of that little tiny box that's the data stuff in it. And you can come up here and increase the font if you need it bigger. Now, alternately, you can actually click on your graph, come to the plus sign, and then point the trend line, click the arrow though, and say more options. That will pull up this menu too, so that you can go to the bottom and add your graph. It'll pull up this menu and then you can do all the usual stuff. Display equation, display r graph, and all that, r squared. There's the bottom two that you need to check though. And notice I'm getting the exact same thing without any formulas. I'm getting the same calculations I just did. So why would anybody ever do it that way? Well, sometimes Excel doesn't give us enough decimals, and it's not always easy to change this to the right amount of decimals you need. So if you do it the formula way, and they want 5 decimals, I can come up here and just quickly get my 5 decimals. And if I need like 4 decimals, boom. And so if I need a higher level of precision, in general, this is easier than doing this method. If I don't need that many decimals, then of course the scatter plot method is probably easier because it gives you everything all at once. Okay, but let's look at our model now. Is it appropriate? Well, clearly r squared is very good. That's bigger than 0.8. The line seems to be going through the data pretty well, right? It's all kind of nice and tight and going up. So the scatter plot looks pretty good. So the only thing we have left to figure out is, are the residuals good? So I'm just going to insert a couple rows. And let's get our residuals. So we're going to need y hat to get our residual. Oops, a little too far. And so our y hat is our prediction equation. And let's see, it says, oh, one other thing I want to notice and tell you here. I do want you to point out that Excel, when it gives you this formula, it gives it to us in the algebraic way. So do notice that if you were to write this equation, you would not write it that way in statistics. We go y hat and we write the intercept first, and then the slope. So be very careful when you're doing the homework problems and you do the scatter plot method. They're going to give you this answer and you have to know to switch them around when you type it in the computer, because we do intercept and then slope. So keep that in mind, that the Excel way does it the algebraic method, and we got to flip them to make it work for statistics, just because we want to be extra in statistics. Okay, but now let's get our y hat. So we have negative 1413.1 plus 24.08 times my input of x. Going to carry my calculations all the way across. And now we're ready for residuals. Y minus y hat, actual minus predicted. I get all of my residuals. And now we want to graph it, right? X values, control, residuals, insert, scatter plot. And uh-oh, look at that residual. What's wrong with this residual? Well, that's very much a pattern, right? We cannot have patterns on our residuals. This is a big old U. So this is a big red flag that there's something going on, that our data is probably not linear, because it makes this U-shaped pattern. And so is the model appropriate? No, because it failed the residual check. We do not want to see patterns in our residuals. All right, my friends, last question of the day. There will be more residual and correlation practice next week. Let's go. So on this one, again, we're doing a least squares regression. That's the only one kind of regression we're going to do, is a straight line regression. And we're given a description, and we're trying to figure out what the original data was. We want to find the original data, interpret the correlation that we get, and then decide if the model was appropriate in the first place. So let's think about this. What would normally go here? We would normally have our x's, our y's, and then our y hats. And they're telling us these are residuals. So we need to figure out these values. And we're given more information. From birth until 18 is our initial thing, is our input. And so that's pretty easy. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up till 18. I know I could drag this down, but why not have a little bit of fun? It looks like I might have miscounted. Oh, I did. Just going to scoot these down because I kind of wrote too high. There we go. Everything matches up now. Okay, so we have our x's lined up. We have our residuals lined up. And so now we're ready to get into trying to find y and y hat. Well, one thing we can do is take advantage of the second sentence. At birth, it starts at 6 pounds, and then it increases by 7.5 pounds. Remember our equation, y hat b naught b1 x, where this is the start and this is the change. So what's the start? Well, at birth, that's when we start, right? It's 6. So y hat starts at 6. Then how's it changing? Increasing, so plus. If it said decreasing, I'd put minus there. By 7.5. So it's changing by 7.5 per year. And now that we have our y hat, notice y hat only depends on x, and we know x, so we can actually fill in this row, that whole column, I should say. So it equals 6 plus 7.5 times x times 0. And I can now, that I did 6 plus 7.5 times 0, I can go back to it and I can generate all of my data. So there's all of my y hats per year. Now remember what these residuals are. The residual is actual minus predicted. Actual is known as y, predicted is y hat. And so if I do this number, minus 6, my answer is 6. So some number, take away 6, is 6. Well, if I do, 7 take away 6 is 1, 8 take away 6 is 2, 9 take away 6 is 3, so on and so on and so on. I can eventually get there, but that's going to take a long time. So we might remember from our algebra days, if we want to find some mystery number, we can get there by just working backwards. If we just add these two things up, we can get our actual value. So that's an important other equation. We know then that residuals is y minus y hat. That means that y is y hat plus residual. We can just add those two together. That also means if I wanted it, y hat is y minus the residual. So we have three nice equations that all naturally come about due to each other's definitions. And in this case, we want y's, and so we just need to add up y hat and residuals. So y hat plus the residual will give me my original value. And yes, 12 minus 6 is 6. Take my data all the way down, and I now have all my data. And if I subtract these, I do get that number. If I subtract them, I do get that number, and so forth. But now I have my stuff. I have my data all done. So we found the original sample data. Let's find the correlation. So we're going to highlight our X and Y data. Insert, scatter plot. And there's my X and Y data. We want our correlation. So let's actually go plus signs, trend line, more options. Let's go to the very bottom. We don't need the equation today because we already have it from the original. So it's going to go display R squared. And so there's R squared. So what if I want to work backwards? Well, if R squared is that number, how could I find R? Well, R squared is 0.9843. And so R is just the square root, right? That's how you get rid of a square root of R. Otherwise, we still have that formula. We could say Corel, and y'all know I'm going to do Y's, and then X's, but yes, I know you can do it in either order. It's just how I always do it. And we get the same calculation. So you have two different methods of doing it. You can take the square root of R squared, or you can just do Corel directly. Anyways, determine and interpret. So we have a, we can see from the scatter plot, a linear, very strong, and positive correlation. Relationship. The reason why I said very strong is, of course, from our formula page here. If we go back, we can see that between 0.8 and 1 is very strong. Okay, is the model appropriate? Well, the scatter plot looks darn good. R squared is very good. So the last thing we have to worry about is the residuals. Well, if I graph my x's, hold down Control and graph my residuals, I can say insert, scatter plot, and look at that. Is it random? Is it all over the place? Yes, that's a great sign. And is it about equally bad? Is it about as many above it as below it? Well, remember, it doesn't be exact, but it should be roughly. And so we have like 3, 6, 8, 10. And down here, 3, 6, 9. So yeah, it's about 50-50 split. And so that's a good sign. We have it about equally bad above and below. We have a randomness to the shape of itself. So this is a great sign that this is a good residual. Good residual, good R squared, good scatter, good model. So yes, the model would be appropriate. All right, my friends, that is residuals and correlations in a nutshell. Next week on Tuesday or Saturday, I'll go a little deeper with this and all that stuff. I hope you saw my message about the upcoming in-person workshops and big final exam reviews, all that stuff. I hope you registered, but if you're not, I understand. Have a great day.